Namaskar. In the last module, we explained about the origin of color of coordination compounds using crystal field theory. The color originated due to absorption of a frequency or range of frequencies of visible zone of electromagnetic radiation. This absorbed frequency or energy of electromagnetic radiation is used to excite electron in the split d orbitals, that is, for the excitation of electron from lower energy level to higher energy level. The complementary color of the absorbed radiation is seen as the color of the compound. However, for all such electronic transition, system must have to follow spin selection rule and Laporte selection rule. According to spin selection rule, during electronic transition, spin of the electron should not change. The relaxation of this rule was found in the case of spin orbit coupling, which we generally seen in the third transition series and in the F block elements. According to Laporte selection rule, in a centrosymmetric molecule, Girardet to Girardet or Ungirardet to Ungirardet transitions are forbidden. That is, in case of electronic transition, delta L equal to plus minus 1 is only a allowed transition. It is therefore transition from S to P, P to D, etc. are the only allowed transition, while P to P or D to D transitions are forbidden. The T to G to EG transition in an octahedral molecule is only allowed in case of vibronic transition. The case is found during asymmetric vibration of octahedral molecule. Since in all other types of vibration, such transitions are not allowed, it is therefore intensity of color of such compounds are very low. Actually, more a system follow the selection rule during electronic transition, more intense color is obtained. It is therefore potassium permanganate is intense in color, as in this case electronic transition occur from p orbital of oxygen to d orbital of manganese and follow both the selection rule. This kind of electronic transition is called ligand to metal charge transfer. However, this kind of charge transfer is not explained by the crystal field theory. The energy of absorption of d transition depends on crystal field splitting, and therefore the factors that affect crystal field theory accordingly affect energy of absorption of light. So, explanation of color of coordination compound you have learnt. There is another important property of transition metals, and this is magnetic behavior of it. In this lecture, we will learn about explanation of magnetic behavior of coordination compounds by the crystal field theory. Till the end of the lecture, you should be able to recognize the magnetic behavior of the coordination compounds, and you should be able to determine value of magnetic moment of coordination compound on the basis of crystal field theory. Transition metals and their compounds show magnetic behavior. The magnetic behavior of transition metal is quite interesting, and therefore their clear-cut understanding is very important. For your curiosity, I am taking an example of a transition metal iron. Iron and its compound show almost all types of magnetic behavior. For example, iron itself and even some of its compound like ferric chloride get attracted in the external magnetic field and show paramagnetic behavior, while potassium hexacyanoferrate repel the applied field and behave as a diamagnetic material. Some minerals of iron, when exposed to external magnetic field, act as a magnet itself and called ferromagnetic. The spinel molecule Fe3O4 contain two different types of iron, that is Fe2+ and Fe3+. Neither make them paramagnetic nor ferromagnetic. Such kind of compounds are called ferromagnetic. And hematite, iron 3+ cation oriented in such a way that the magnetization of one iron is getting cancelled by the other. Such types of compounds are called antiferromagnetic compounds. All these magnetic behaviors are generated by single metal iron. No doubt, the magnetic behavior of compounds are very important in these days of industrialization, and therefore understanding magnetic behavior is equally important. So let us first learn about the origin of magnetic properties. If you remember, in physics you have learned that any charged particle, if complete a loop, then it generates a magnetic field. Protons and electrons in an atom are the charged particles. They complete a loop by three different ways: nuclear spin, electronic spin, and orbital motion. In case of nuclear spin, nuclei having odd number of protons or odd number of neutrons or both generate a net magnetic moment. Since nuclei spin on its own axis, all the nucleons can be assumed to complete a loop, and therefore magnetic moment is generated by the nuclei. Case 2, when there is electronic spin, so electron is a negative charged particle and spin around its own axis. A spin can be considered as a circle or a closed loop of infinitesimally small radii. Therefore, a spinning electron generates magnetic field. It is to be noted that magnetic field is associated with the direction. If you have another electron of opposite spin in the same orbital, obviously direction of magnetic field generated by these two electrons will cancel each other and no magnetic field will be generated. So only an unpaired electron generate magnetic field. Now let's discuss about the orbital motion of electron. Electron, in order to occupy the entire spherical space around nucleus, move from one orbit to other in its own degeneracy and therefore complete a spherical loop. For example, p subshell contain three orbitals px, py and pz. An electron move from px to py to pz and then come back to px. By this way, electron covers the three-dimensional space around nucleus. So, if electron covers this kind of loop, magnetic field generates. The nuclear magnetic field is around 1837 times smaller than the electronic magnetic moment, and therefore in this lecture, for all the purposes, we will ignore nuclear magnetic moment. The magnetic field produced due to spinning electron may interact with each other and with an external magnetic field and produce interesting magnetic behavior of atom or molecule. When I say magnetic field of electron interact with each other, I mean to say the magnetic moment, or more precisely magnetic dipole moment of all the electronic motion of a single energy sublevel coupled together to produce spin only magnetic moment. This kind of coupling is called spin-spin coupling or SS coupling. Similarly, angular momentum by electrons of an atom may couple together to generate total angular momentum quantum number. Such coupling are called LL coupling. Also, magnetic moment generated by total spin and total angular momentum may couple together to produce a net magnetic field. Such kind of coupling is called SL coupling or spin angular momentum coupling. So, let us first discuss about the magnetic moment generated by total spin of transition metal and associated cases of the coordination compounds with it. If S is the total spin quantum number of atom or ion, the value of magnetic moment is determined by the formula considering spin-spin coupling only would be mu s is equal to root under 4s into s plus 1 Bohr magneton, where S is the total spin of the atom or ion which is generated due to sum of spins of unpaired electrons only, as spins of paired orbitals become 0. Since spins of each of the unpaired electron is plus half, it is therefore mu s is equal to root under 4 into n by 2 into n by 2 plus 1. This will become root under n into n plus 2 Bohr magneton. Here n is the total number of unpaired electrons. Bohr magneton is the unit of magnetic moment having formula Eh by 4 pi mc, where E is the charge of electron or charge of the charged particle, H is the Planck's constant, m is the mass of electron, and c is the velocity of light. The numerical value of Bohr magneton comes to be 9.274 into 10 to the power minus 24 joule per Tesla. Now let's see a situation and analyze its crystal field explanation. The question for you is, FeCl6 4 minus is a paramagnetic with a magnetic moment around 5 Bohr magneton. But same ferrous ion when form complex FeCN6 4 minus, it becomes diamagnetic with magnetic moment 0. According to crystal field theory, chlorido is a weak ligand and therefore form high spin complex with ferrous ion. It is therefore the electronic configuration in split state of d orbitals become T2G4 Eg2. This gave a total of 4 unpaired electrons. So according to the formula mu s equal to root under n into n plus 2 Bohr magneton, value of magnetic moment becomes square root of 24. This value becomes 4.9 Bohr magneton, which is very near to the value given, that is 5 Bohr magneton. On the other hand, cyanide is a strong ligand and therefore form low spin complex with the configuration T2G6 Eg0. You all know T2G contains 3 orbitals and 6 electrons in its make all the orbitals paired. At the same time, Eg orbital do not contain any electron. So value of magnetic moment becomes 0. Now let's discuss about the magnetic behavior generated due to orbital contribution of the electrons. LL coupling. The magnetic moment is also generated due to LL coupling. Capital L represents sum of all ml values of electrons of the atoms. For example, the capital L value for D2 configuration in unsplit state is +3. This is because first electron is contained in d orbital of magnetic quantum number +2 and the second electron is in orbital with magnetic quantum number +1. As a result, total 2 plus 1 equal to 3 is the value of capital L, that is the value of the total angular momentum quantum number. Now, according to formula, the magnetic moment of an atom or ion because of contribution of spin and angular momentum is mu SL is equal to root under 4s into s plus 1 plus L into L plus 1 Bohr magneton, or mu s is equal to root under n into n plus 2 plus L into L plus 1 Bohr magneton. Though in most of the cases of the first transition series, we do not get this much of the value of magnetic moment. This is because of quenching in orbital angular momentum. What is quenching? For example, if electrons move from one orbital to other, and in this connection, if there is no any net change, orbital angular momentum are called to be quenched. For example, if in a p2 configuration, single electron is filled in px and pz orbital, so if electron moves from px to pz, there is no net change in the orbital angular momentum. But the same is not true when electron move from px to py or pz to py. It is therefore we call 33.3% of orbital angular momentum is quenched, and only 2/3 of total angular momentum will be available for generating magnetic moment. Now let's solve a problem on magnetic moment of coordination compound and see the crystal field explanation of the same. The magnetic moment of the molecule NiCl6 4- is less than the magnetic moment of NiCl4 2-. Explain why. Before answering any of such question, let us first draw the crystal field splitting of the same. In both the cases, chloride is the ligand, which is a weak ligand. It is therefore NiCl6 4- is a high spin octahedral complex, while NiCl4 2- is a tetrahedral complex. Drawing crystal field splitting diagram of NiCl6 4-, we get the configuration T2G6 Eg2. As a result, we get two unpaired electrons. Similarly, when we draw crystal field splitting diagram for NiCl4 2-, the configuration becomes E4T24. Here also we get two unpaired electrons. So, the reason of higher value of magnetic moment must be involved with the value of angular momentum. You can see in case of octahedral crystal field splitting, T2G orbitals are completely filled, and therefore because of their uniform filling, no magnetic moment should be generated through T2G orbitals, while Eg orbitals are half filled, that too is symmetrically filled. So, there won't be any contribution through angular momentum by both the orbitals. On the other hand, in case of tetrahedral splitting, the configuration in split state becomes E4T24. Here, E orbitals are symmetrically filled, but T2 orbitals doesn't. It is therefore a contribution from angular momentum comes in case of tetrahedral arrangement of same metal ion. This makes value of magnetic moment of tetrachloridone nickel 2 plus higher than the magnetic moment of hexachloro nickel 2. One question is needed to be solved through crystal field theory is that why NiCl4 2- is diamagnetic but NiCl4 2- is paramagnetic. I leave this question for your exercise. Here is the table in which you can see the value of magnetic moment for high spin and low spin octahedral complex due to contribution of spin only magnetic moment. The value of magnetic moment for tetrahedral arrangement of D3, D4, D8 and D9 complexes is found higher due to less effective quenching of orbital angular momentum. So, we have seen many applications of crystal field theory that are itself able to validate the proposed theory, but still there were some findings that were unable to be explained by this electrostatic model. So, let us discuss about the successes and limitations of crystal field theory. So, first discuss about the successes of crystal field theory. Crystal field theory successfully explain why metals and ligand combine to form megastructure of coordination compounds. The theory explained the cause of formation of low spin and high spin complexes. The theory correctly ordered the strength of the ligands. By the help of this theory, we become able to determine value of magnetic moment, for which we were not able to determine by all the previous theories. It explained values of appearance of color in transition metals and in their complexes. Anomalies in trends of ionic radii, hydration energy and lattice energy of transition metal ions and their compounds were successfully explained by this theory. The theory successfully explained formation of spinel and inverse spinel structure. Now, let's reach to the limitation of the crystal field theory. The assumptions of considering metal and ligand as pure charged particle are not look very realistic. Actually, they are not exactly a particle. The theory only predict splitting in d orbitals and doesn't explain any such splitting in other sublevels like S or P or F sublevel. The theory arranged the ligand in accordance with its increasing strength, but this theory is unable to explain if ligand is a negative point charge and this negative charge is giving repulsion to metal d orbitals, then why hydroxyl ion ligand or hydroxo ligand is weaker than a aqua ligand. Similarly, water is more polar than ammonia, but water is called as weaker ligand compared to ammonia. No any suitable reason were provided by crystal field theory for these things. Possibility of covalent interaction were discarded in this theory, because of which metal to ligand charge transfer and vice versa is not predicted by this theory. The theory explained the D transition as an origin of color of coordination compound which is Laporte forbidden and has very weak intensity. But it doesn't accounted charge transfer from ligand to metal or metal to ligand, which gives intense color and follow all the selection rules. The theory explained a bit about color of the complexes but was not explained the electronic spectra of the compounds. The crystal field theory explained magnetic behavior of compounds on the basis of splitting of d orbitals in ligand field, but doesn't explain any anomalies due to electron transfer from metal to ligand and vice versa. Transition metals on forming coordination compound also show diversity in magnetic behavior. Crystal field theory were found able to justify the values of magnetic moments to a larger extent. Most of the anomalies were solved by seeing crystal field splitting pattern. The theory satisfactorily solved the value obtained for spin-only magnetic moment. It doesn't provide any reason for the compound for becoming ferrimagnetic, ferromagnetic and antiferromagnetic. So, crystal field theory was successful in explaining origin of color, magnetic properties of coordination compounds. It also explained anomalies in trends in ionic radii, enthalpy of hydration and in lattice energy. The cause of formation of spinel and inverse spinel structure found by transition metal were also explained by this theory, but was unable to explain sigma and pi bonding between metal and ligand. Electron transfer from metal to ligand or ligand to metal is also not explained. Also, the model didn't explain the cause of increasing strength of ligand in spectrochemical series. Electronic spectra and the complete magnetic behavior of coordination compounds were not explained by this theory. So, it is quite obvious that though the theory has certain successes, but some behaviors which were not explained by it need a better and complete theory for understanding. In your higher classes, you will learn molecular orbital theory that incorporates all missing part of the theory and were found to have wider applicability. Thank you very much for listening this lecture. Thank you.